So thanks for coming. Today I'm going to be talking about some work we did at GitHub last year to move tables across clusters. And this was an effort towards scaling our high traffic database. So nice to meet you, everyone. My name is Bryana Knight. I'm a developer on the database services team at GitHub. Bryana Knight on Twitter. I'm also a tech lead for Women Who Code Boston chapter. And last year I spoke at RailsConf and SyntaxCon about some other database performance topics. So first off, I just wanted to give like a bird's eye view of our GitHub application and the way that we communicate with our database. So at GitHub, we have a Rails monolith, which talks to our MySQL database. So within our database, we have multiple clusters, each of which hold a certain subset of tables. So for example, here we have our cluster 5, which holds some events tables. So anything that you do on github.com could trigger an event, like closing a PR, commenting on an issue, pushing up some commits. So we're going to log that into our cluster 5 here. And so each cluster has a master and some replicas hanging off of it. And we try to funnel as many reads as possible to our replicas. And then obviously the master will handle all of our writes that are coming in. So another example over here, we have our KV cluster, which holds some key value data. We have our cluster 2 over here, which stores some notifications table. And then we have our MySQL 1 master cluster. So this is our main cluster within our MySQL database. It holds all of the central tables that you might think about when you think of github.com. So things like users, repositories, issues, permission data, that's all stored in MySQL 1. So this is far and away our busiest cluster. To give you some numbers, I think we funnel about 95% of reads to replicas here. So there is still a small percentage of reads that are going to go to our master. So this is the cluster we're going to be focusing on today. This was giving us some trouble. So we really needed to take some action in order to remedy that. So just to set the stage of where we were. So there were several availability incidents in a short period that were caused by pressure on our database, specifically the master server of our main cluster, MySQL 1. So anything that caused a higher than usual load posed as a risk for us. So this wasn't a great place to be in. We knew that we needed to act fast, but make enough of an impact to give us some medium-term breathing room. I'm not going to go into too much detail about how we got here. We just celebrated our 10-year anniversary, and GitHub has been really lucky that we've seen a huge amount of growth in that time. And we have this Rails app that has served us really well. It allowed us to get to the place that we're in, but it is a monolith, right? So that is going to reflect itself in our database. So it was just like an organic growth that got us to this point. And I think this is something that a lot of companies have to deal with. Everything kind of just caught up to us at one point. So we know we needed to make some changes. So what did this look like? So here we could see an increase in load that's kind of out of the norm, right? So we have these rows inserted, and that like basically doubles here. So that's not something we're used to seeing. So we see some sort of large increase in updates, writes, deletes, any write action. So that increase in load means that there is some sort of big uptick in updates or deletes or writes or anything like that, and that can cause replication lag, right? So if you think about this logically, that data is being written, it's being deleted, it's being updated, that needs to be replicated out to the replicas, right? So that causes that lag, right? It takes longer for the replicas to catch up because there's an increase in the data that's changing. It can also lead to a spike in MySQL threads running. So this kind of has a waterfall effect, right? It cascades to other parts of our system. So replication lag can lead to a decrease in job throughput. So when I talk about jobs, I mean background jobs. So when a request comes into GitHub, we try to put as much as we can into the background, right? So any action that can be taken that doesn't need to complete within the process, we can push towards the background. So within those background jobs, we also gain the ability to throttle, right? So since that action doesn't have to happen instantaneously, we can take into account the replication lag at that time. So if replica lag is high, we're going to throttle and we're going to pump the brakes a little bit on whatever action we want to continue with. So that's probably a write or an update. So when replication lag is high, these jobs take longer to complete because we're waiting for the replication lag to subside. And so this just leads to a backup in jobs. And some things that we have in our job queues are things like notifications delivery and some UI updates depending on what that page is. So this ultimately can lead to not the best user experience. So this is Jonah. Jonah's really wise, and I think he put this really well. He stated that high load on the master is less immediately obvious, but also user visible. So when it's bad, it means that GitHub is slow. When it's really bad, it means that GitHub is entirely unresponsive. So we decided to move some tables out of our main MySQL 1 cluster in order to move that traffic out of the main cluster so that it wouldn't have this cascading waterfall effect on our system, right? So what makes a table a good candidate to move? So we were looking for a relatively high rate of reads and, more importantly, writes, so that the impact of moving it off the main cluster was significant enough. Few or no joins with other tables. So you can't join tables across clusters. So we were looking for tables that were decoupled enough that it would be feasible for us to move them out of the main cluster. And then another thing we were looking for was that the writes can be backgrounded or they already are. So I'll go into detail about this later, but we essentially wanted the ability to be able to control when the writes are coming in. So we would be able to pause them and resume them if they were in queues within background jobs. I needed to change some of the names of the tables, and I think Shlomi made this joke a couple of years ago at Percona. And he said that GitHub is just a swag shop, and we just peddle T-shirts and water bottles and things like that. So that's what we're going to go with for the remainder of this talk. So the first table that we decided to move was the coffee mugs table, and we were going to move this into the beverage cluster. So coffee mugs, it was one of our largest tables. There were only a few joins. The writes already all came from background jobs. So this presented itself as a quote-unquote easy first table to move. So I just wanted to go into a little bit of detail about how we split joins, because that was something that we needed to do before moving any table. So here we have a pretty basic query. It's just asking for all the gift bags with small coffee mugs that have the Octocat logo. So at the top here, we have the active record query, which is just the ORM that Rails uses. And then below, we have the SQL equivalent. So we're just joining the gift bags table on the coffee mugs table based on the gift bag ID. So to split that, we would just grab the gift bag IDs from the coffee mugs table for records that satisfy those conditions, and then feed them into a separate query to the table with the data that we actually need. So obviously, you're going to take a bit of a performance hit when you're making 2 round-trip queries as opposed to 1 join query. That was something we were aware of and something that we monitored. But we knew that we were OK with a slight performance hit as we were working towards the goal of moving this table out. So I just want to go into the details of what we needed to do from the application's perspective and then from the database's perspective to make this happen. So the first step was to split all of the joins or unions with the table that we wanted to move, background the writes, and put those jobs into a separate queue that we would have the ability to pause. Then provision a new cluster, and then start replicating from MySQL 1. And we would just replicate the table that we needed into that new cluster. And this was the most efficient way to get that data into the new cluster ready and waiting for us. And then from the application's perspective, here we needed to make our model establish a connection to the new cluster. So as you can see here, we're establishing a connection, a read-only connection, and a primary connection to the new cluster here. But the big caveat here is that we're actually still pointing the environment variable that's behind this connection to MySQL 1. So we could cut a PR, make that change, ship this code, and everything still just works because it's still going to the table in MySQL 1 at this point. But we have this new connection defined that we can use. And then, actually, in our Rails application, we do some raw SQL queries. So we have active record queries and SQL queries. So we needed to create a SQL client, a custom SQL client that would use that same connection, and then update all of the callers of SQL queries going to the coffee mugs table to use that custom SQL client. So at this point, everything is wired up, but we're still pointing to MySQL 1 for everything. So now for the actual cutover. The first step was to switch the read-only connection to point to the new cluster. We did this by changing that environment variable that I said. Then deploy to a staging environment, test in staging. We could make sure that pages were rendering. We could hit the API there, and make sure that those read-only queries were hitting the new cluster. Then deploy to master, so that environment variable change is picked up everywhere. And then we could just make sure via Datadog and Vivid Cortex that all of the read-only queries at this point are going to the new cluster. So all set for reads. Just to give you a visual of what this looks like, we have that reader host defined there that is pointing at the old cluster, and then we just update that to point to the new cluster. So now for the writes. This is where it gets interesting. So we would pause the queues with all of the backgrounded writes. So at this point, we have no writes coming in to that table. Then update some configuration. So we detached the replica and made it writable. So at this point, we could do writes to it. Then we dummy dropped the coffee mugs table in MySQL 1. So that's just a rename there. So at this point, once again, no writes coming in, and that table no longer exists in MySQL 1. Then switch the primary connection to point to the new beverages cluster, deploy to master, resume the writes. So at this point, they'll all be hitting the beverages cluster, and then change your shirt because this is really scary. So just to go into a little bit even more detail about how we did this. So once again, the first step was pausing all the jobs. We actually did that via chat ups. We have some awesome chat ups at GitHub. Then detach the replica, dummy drop the coffee mugs table in the main cluster, also via chat ops. Set read-only off on the beverage cluster, change the value of the MySQL beverage writer host environment variable to point to the new cluster, and then set the role as master. And then finally, do a puppet run, then resume the queue so that writes start to come in again, and then reset the master replication. So I think it's really beneficial to see this visually to understand how it's working, right? So we have our GitHub application up there that is where all of our queries are coming from to this coffee mugs table. At this point, we haven't done anything. So the read-only queries are going to the replica in MySQL 1, and then we have the backgrounded writes going through rescue to hit the master. So the first step is to start replicating into the new cluster. So all that data is there and ready for us. Then switch the read-only connection, right? So that was really simple. We just changed the value of that environment variable. So now we have all of the read-only queries going to a replica in the new cluster. Then pause writes, so no writes are coming in at this point. Cut off replication, promote the new cluster. Drop the table from MySQL 1, then resume writes. So at this point, everything is going to the new cluster. So this is where we land. Oh, yeah. Unfortunately, this was not a perfect strategy. There were some pitfalls that we ran into during the cutover, so that made it even more fun. So as I stated, we needed to update all of the callers that were doing SQL queries to the coffee mugs table to use that custom client, right? So there was one write query going to the coffee mugs table that was not using the correct SQL client. So this was just human error. But with this strategy, we were vulnerable to human error, right? So this just meant that we needed to cut a PR mid-cutover and then deploy it. So it wasn't the end of the world, but something unexpected that popped up. Another thing was, when we paused the queues with all of the backgrounded writes to the coffee mugs table, we had paused all the queue with those background jobs, but there were background jobs in other queues that were still running that were triggering individual background jobs in that queue. So even though the queue itself was paused, individual backup jobs within that queue could still run. And we hadn't really anticipated this, so we actually had to pause more queues than we thought. So that just led to a decreased user experience because we were pausing queues that we didn't expect that we had to. And then I think the biggest pitfall here was that we were dependent upon deploys. And unfortunately at GitHub, deploys are not super fast. So this just prolonged the process of the cutover. I think in the end it took a full hour to just you would think it was a switch of a button, but it wasn't. But we did love the effects that this had, right? So immediately after we dropped this table from MySQL 1, we could see that the IO read and the IO write, it just looked great to us. And we wanted to keep moving tables. So we decided to iterate, right? Like, how can we improve this process but still use it? So we wanted more confidence that we were using the correct connection to the right cluster everywhere. So the first step was to get the multi-cluster setup in test and development. That's not something that we had. So we were really prone to those human errors because those things wouldn't show up in tests and in development. So we spent a lot of time getting that set up. And this was just generally a good thing, even if we weren't going to be moving tables, because this was prone to errors for application engineers as well. Another thing we did was we added kind of a lint test that would subscribe to SQL queries for whatever table we were trying to move, and then we could assert in those tests that the connection that we wanted to use. And then I think the biggest improvement was that we decided to rely on a feature flag to change connections from one cluster to another, as opposed to just depending on that environment variable change. So this allows us to gradually enable that feature, in this case, the new connection, and then we could change that in the UI or via chat ops, as opposed to waiting on a deploy. This is an open source tool. It was developed by one of the engineers at GitHub, and we actually use Feature Flipper for pretty much every change at GitHub. So it's a really safe tool. MySQL.
But is it the same cluster that you
It's in MySQL 1. As is everything. So the next tables that we decided to move were the t-shirts table and the hoodies table. So we were going to move these into the bestsellers cluster, which was a new cluster. So t-shirts was top 5 in write rate, top 10 in write total time, and then all of the queries were in one place. So this was a big thing for us because we didn't have to take the time to track down all the queries in our huge monorail. Hoodies was a bit bigger. It accounted for 4% of master writes and 3.5% of master reads. So once again, pretty much the same steps: split the joins, background the writes, provision a new cluster, and use replication. But in this case, when we made the new configurable SQL client and changed the model, we just set the connection based on that feature flag, and then update all the call sites to use that client in the model. So I just wanted to show you in the code what this looks like. So here we have this transitional hoodie model, right? And that's going to define the read-only and the read-write connection based on a feature flag. So for the read-only connection here, we're just checking whether or not that feature flag is enabled. If it is, we're going to use the connection to the new cluster. If it's not, we're going to fall back to the connection for MySQL 1. And then our hoodie model that we're going to be using, it inherits that connection configuration, and we still have all of the things that were in the model previously, like callbacks and validations and things like that. And then for our SQL client, we're just going to use that same connection that we established here. So now for the cutover. So this is much simpler now with these improvements. So now we can slowly enable the reads feature flag to gradually move reads to the bestsellers cluster. So we did 5%, then up to 10%, everything looked good, 20%, 50%. And since these are just read-only queries, this works because they're basically just going to another replica at this point, even though that replica is in a different cluster. So this was really great because we could see gradually that more and more read-only queries were going to the new cluster via Datadog and Vivid Cortex. So for the writes, pretty similar. Pause the queues once again, detach the replica, make it writable, dummy drop the table in MySQL 1, watch for needles, which are just exceptions. And then at this point, we need to fully enable the writes feature flag to move all of the writes over to the new cluster. We cannot gradually enable this because we can have some writes going to MySQL 1 and some writes going to the new cluster. So everything, this is like an all or nothing point. Then resume the queues so the writes continue, and at this point, they should all be going to the new cluster. And then it's still very scary. So even though we made all of those improvements, it was not perfect. So I think we got some tunnel vision in this process where we kind of forgot that read-only is not all reads. So when we dummy dropped the table from MySQL 1, we did that before enabling the writes feature flag, which actually should have been called the primary feature flag. So there was like a non-read-only read that was still trying to go to the table in MySQL 1, and we had dropped it at that point. So we kind of had to pause and figure that out. But since it was a dummy drop, we could restore that table and take the time we needed. So even with all those improvements, we knew that this approach was still not perfect. So we took a step back and we said, should we keep using this strategy? We knew it was still risky. We didn't love that we had to background and pause these writes, even though it was like something that we could do because the writes were pretty much backgrounded already. Having to pause those queues led to like not the best user experience. And also for a lot of the other tables, I think most of the other tables, we couldn't background writes. Like most tables, you can't do that. We also knew that we shouldn't keep provisioning new clusters. Like we had provisioned these 2 new clusters, they had plenty of space. So we wanted to move tables into them. So we knew that there had to be another way. So knowing that, we set our sights on the stickers table. So the stickers table accounted for over 10% of reads to the master. It was about 7% of writes. At the time, it was about 1.5 billion rows. But there were no joins, and there were no updates. So that made it really appealing for us to move. So I just wanted to explain that a really important point here is that stickers only exist in the context of sticker packs. So stickers don't really, in this example, stickers don't really exist independently. The only way you can get a sticker is by getting a sticker pack. Okay, so we decided to go with a temporary sharding strategy. So the way that works is that we would utilize a lookup table that stores information about which sticker pack stickers are stored in which cluster. Then we would do a lookup against that table before any stickers query, and then we would gradually copy sticker records into the new cluster and update that information on the stickers in the lookup table. Then we would do that until there weren't any reads or writes going to the table in MySQL 1, and then at that point we could drop the MySQL 1 stickers. So what are the advantages of this strategy? So we were able to move stickers in the context of sticker packs. So sticker pack ID is essentially our shard key here. Every query that's going to the stickers table has where sticker pack ID equals whatever. We didn't have to pause writes. No environment variable changes to do connection switching. A big advantage was that this was fully testable, right? So we can create some dummy sticker data. We can test the routing logic. We can test the transition, the copying of the data into the new cluster and make sure that all works before doing this on any other production sticker data. Also, we would see a gradual increase of traffic onto the new cluster and off of MySQL 1 as this was going on. And then finally, we kind of had to do it this way because we couldn't use MySQL replication. Since we were moving this data into an existing cluster that was already serving writes to other tables, we couldn't really use MySQL replication to get that data into the existing cluster. So we had to move it ourselves. So your next question might be, how the F did we copy 1.5 billion records and preserve data quality and still serve every single query coming in and not bring our site down? So I just wanted to show you some code. So at GitHub, whenever we have to do some sort of large amount of operations on data, so backfilling data, fixing a data quality issue, doing a ton of inserts, doing a ton of deletes, we use what we call a database transition. And database transitions provide us with some safety guards. So we always iterate in batches and do those updates in those batches so we're not doing it on a ton of rows all at one time. We go to the read-only replicas for reads to get that data, and then we throttle, which is the most important thing. So we're taking into account replica lag. So if replica lag is high, we're not going to add on more load here. So I just wanted to explain this visually once again. So here we have this sticker service, which is just a class within our monorail that has all of the queries going to the stickers table. Then we have the stickers table in MySQL 1 with all of the data. And then we have an empty stickers table in the bestsellers cluster. We also have this stickers routing table, which I alluded to before. So this table holds a sticker pack ID and then the name of a cluster. So when a query comes in, it asks, where should I route this query for sticker pack 1? At this point, the routing table doesn't have any information in it, so the routing logic says, we haven't touched that sticker pack stickers yet, so go to MySQL 1. So it's going to resolve the query by using that connection. In the meantime, we're going to start up this transition that's going to start copying this data over. So the transition is going to copy the stickers for sticker pack 1, and then it's going to update the routing table and say, I'm done copying, update sticker packs 1 cluster to bestsellers. Then when that same query comes in, the routing table says it's in bestsellers, so the logic will route that query to the bestsellers cluster. And then in the case of when we're in the process of moving a sticker pack stickers, right? So some sticker packs have 5 stickers, some sticker packs have like 5 million stickers, so it might take a long time to copy all of those records. So the transition will update the routing table to have that cluster be moving. So when that query comes in, it says, where should I route this query for sticker pack 2? The routing logic will say, we're in the process of copying, read from MySQL 1 and write to both. And remember that there's no updates, right? So we don't need to worry about updating that data. So we're going to write to both places, but we're going to read from MySQL 1 because potentially not all the stickers are in the bestsellers cluster yet. So as this transition was running, we were monitoring like a ton of graphs. So as you can see here, the rows inserted into the stickers table in the new cluster, that spikes a lot as this transition is running, and then it tails off as it finishes. The rows inserted into the MySQL 1 stickers table gradually decreases, right? Because we're not going to be inserting into there anymore as we're moving stickers over. At the same time, just the count of the rows in the stickers table in the bestsellers cluster, that's just going to increase and increase. At the same time, the IO write in MySQL 1, that's going to go down. The dips are the weekends. And same for the read. And then the IO write in bestseller, since we're doing all those inserts, as the transition is running, that's going to be really high, and then it's going to tail off as the transition ends, and we're just in the point of normal traffic here. So when we started, the stickers table accounted for over 10% of reads, 7% of writes to our master in our main database, and now they represent 0. So, just to sum up, we moved 4 busy tables out of our main database cluster into 2 new clusters. And all of the traffic to those tables now doesn't affect our master database whatsoever. It doesn't have that cascading effect that's going to affect other parts of our system. We used 2 very different but successful strategies. So the first one was MySQL replication. We would pause the writes, and then we would switch the connections, and then unpause writes. The second one was the temporary sharding and the gradual copying of the data. So just some takeaways here. Well, we haven't really had any availability incidents from load on our database that have brought us down since we did this. We did it iteratively. So the first couple times it was kind of quick and dirty. We learned from that, we iterated. And every time the circumstances were a bit different, right? How that data in the table was accessed, whether it was isolated or not, could we provision a new cluster or not, things like that. We didn't really do anything that crazy. We did the simplest and the most effective thing we could do to get us to where we wanted to be. And I think the biggest takeaway is it gave us the time and the room to think long term. So we want to get to a position where, obviously moving tables out manually doesn't really scale that well. So this gives us the breathing room to be able to think about how we want to plan for the future and to start implementing something that will get us there. That's it. Cool. Does anyone have questions? Yeah. Yeah.
First question, you mentioned casually that during a cutover you had to send a PR and then deploy it. If you were having problems with GitHub, how can you send a PR?
We weren't having problems at the time of the cutover.
Okay.
Yeah.
But if you were moving, since you're GitHub and you develop on GitHub,
Yeah.
you move your data and then you take your database down for some reason. How do you have it, like, how do you deploy code at that point in your, like, just...
Well, so when we were doing the cutover, when we saw a problem, like we weren't at the point that we couldn't like roll back whatever change we had just made. So I think when we ran into the problem where we had to cut the PR, it was because we had dummy dropped the table, but we had just dummy dropped it, so it was just a rename. So we could restore it really quickly. Everything's fine at that point, and then we can cut the PR. But we did not do the cutover when we were experiencing any sort of problems. So yeah, does that answer?
Yeah.
Okay.
And I guess second thing is not really a question, but you were looking at long-term plans.
Yeah.
I'm going to be presenting on Ghostwriter in a few things. I think you'll be happy to see that. That'll probably help you.
Cool. Awesome. Yeah.
Did you leave the shard lookup table in place, or did you remove that?
We did not, because I kind of joke, it's like we temporarily sharded in order to like vertically shard permanently. So it's funny because like this was like on a very basic level, like how sharding works. So we could have left it, right? We could have left half the data in MySQL 1 and half the data in the new cluster, but you know, our eventual goal was to move everything into the new cluster. But yeah, it was a good learning experience for sure. Yeah.
What size of the table is
I'm not sure. Well, like all of the tables were of varying sizes. The stickers table was by far the biggest, but I'm not sure. Yeah.
And then why didn't you consider sharding as
Sorry.
why didn't you consider sharding as the final solution?
Like, why didn't we keep it sharded? Because, I mean, our goal in the beginning was to get all of the traffic onto this table out of MySQL 1. We could have left it sharded for sure, but like that means that there's still traffic coming into that table, and that's going to affect our main cluster. So yeah, I mean, if our goal was to shard, we would have left it sharded, but our goal was to get the traffic out. We want to shard. So, yeah. Yep.
You were talking about queues. Were you using, when you were pausing your queue, were you using a malicious queue like a rabbit or Kafka?
Rescue. Cool. Yeah.
Strategy one, the replication, were you using replication filters or were you using like black hole engine on the...
As replication filters. Yeah.
When you were pausing your queue for writes, what was the end user seeing during that? Like, were you already committing the change, being like, oh, it's okay, but you technically not?
No, we didn't commit the rights. So like anything that's in a background job in a queue, that's something that doesn't have to happen right away, obviously. So like, I think the best example is notifications delivery. So you do something, whatever, you close a PR, right? And then we queue up a job that will send an email, right? And so maybe that email happens instantaneously, but maybe it happens 5 seconds later, maybe it happens 5 minutes later. Obviously 5 minutes later isn't the best, but it's okay. Any other questions? Cool. Thank you.